Okay, welcome back to lecture 8.4. This will be the last of lecture 8, where we're going to talk about the work along an adiabat. Okay. So last time we derived our equations for how the thermodynamic variables will behave along an adiabat. So this time let's start by drawing a compression experiment on our PV diagram. So let's imagine starting at a volume 1 and moving to a volume 2. Okay, so this will be pressure 1. So imagine first we had an isotherm, right? It would have gone to volume 2. But if we have an adiabatic, what we'll see is that the curve is actually steeper. Okay, so this is an isotherm, and this is called an adiabat. Now, I was not intending to, there you go. It's not a straight line. It's supposed to be curved, but with a steeper slope. All right, so the equation describing that, remember, was that P times V to the gamma equals a constant. Or the pressure is like a constant over V to the gamma. So along an isotherm, remember? So along an isotherm, we had basically P was a constant. So this is an adiabat. And this is an isotherm. So we had a constant, which was nRT, but T was constant, right? Over V. This was come from our equation of state, right? PV equals nRT. nRT is a constant. So you can see since gamma is always larger than 1, this is going to have a steeper slope for the adiabat than it is for the isotherm. Okay. So now what I want to do is I can see, since I have a steeper slope here, I'm also going to have more work done along an adiabatic compression. What is that work? Right? So remember that the work is the integral of minus P dV. Okay. And I want to know the work in moving from this state to this state, right? So let's write that as the work going from 1 to 2 is equal to minus the integral from V1 to V2 of P dV. Okay, P cannot come out of the integral because P depends on pressure, right? So what are we going to write? Well, we know that PV is a constant along an adiabat, so actually we can do a pretty cool little trick. We can realize that the pressure times the volume gamma, so if I were to imagine picking this point, it's also along my adiabat, so I know that the constant that it's equal could be P1 V1 to the gamma, right? Where this V is a variable, but these were the initial values. Right? And that could be my constant. So now I can write that the pressure is equal to P1 V1 to the gamma V to the minus gamma. So my work going from 1 to 2 is equal to minus the integral from V1 to V2 of P1 V1 to the gamma V to the minus gamma dV. But P1 V1 to the gamma is a constant, so we can take that out, right? We can just pull that right out of our integral. So this is minus P1 V1 to the gamma, integral of V to the minus gamma dV from V1 to V2. Well, we know how to do this one. We can kind of think of this as the antiderivative, right? So if we were to have the derivative, we would have to take this and bring it down, right, and subtract 1. So now we realize to get this, we would have to have minus, let's give ourselves a little space, minus P1 V1 to the gamma is going to be V to the minus gamma plus 1. But if I had taken this derivative, I would have this on the bottom, or I would multiply that out. So I need to divide by minus gamma to the plus 1. Now, of course, I need to evaluate this. Right, so this will be from V1 to V2. And so what we're going to have, just check 1 minus gamma, gamma. Yeah. So we can say that this is, so let's get rid of that minus sign. This is going to be P1 V1 to the gamma, 1 minus gamma. I just took the minus signs out. And this is going to be V2 1 minus gamma minus V1 1 minus gamma. P1 V1 to the gamma, gamma minus 1. I have a different minus sign in my notes. Let me pause and take a look and see what that is. Okay, I see. I did this wrong. This shouldn't have been 1. I shouldn't have done that. It shouldn't have been 1 minus gamma. That's the same. It should have been minus, so it should have been gamma minus 1. Okay, that's good. That's our answer. Okay, that's our work along an adiabat. Okay. So could we have calculated this another way? For sure. Let's invoke the first law. Okay, so first law is pretty powerful with an adiabat, right? Because if we have du equals dw plus dq, right? We know this one's 0. So we have du is equal to minus p dv for a reversible process. Okay? And so our work, right, is simply going to be the change in u, right? So we actually did it more like this now, but let me just think about it like this. Since the heat is 0 and I do this integral, my work done is simply going to be the change in the internal energy. Okay, so that's pretty cool because my internal energy is a state function and I know my internal energy. Remember we had CV was 1 over, so let's just, I think we can do it in terms of, yeah, CV is 1 over n partial u partial t, or du was n CV dt. Okay, so if I want to integrate that, I'm just going to get delta u is n CV delta t, right? Because CV doesn't depend on t, I can actually take it out and I can write this integral like that. And so our work is simply going to be n CV delta t. Now, we can rewrite, so that's pretty nice, but we can rewrite this in terms of instead of CVs, in terms of our R's, right? So gamma was CP over CV, right? Which was equal to CV plus R over CV. Or you can say that this is 1 over R plus CV, right? So we can rewrite our CV simply as, so let's write this as R over CV equals gamma minus 1, or CV equals R over gamma minus 1. And so in that case, we can write our work is equal to N R over gamma minus 1 times T2 minus T1. Another thing to write though is, so since this is nRT, we know that PV equals nRT, so we can write this as PV P2 V2 minus P1 V1 over gamma minus 1. Okay, so that's probably the form we'll use more often. It's a little bit cleaner than that other form, right? So this is a nice form. The work is P2 V2 minus P1 V1 over gamma to the minus 1. Okay, so the last thing we're going to do is we're going to stop and we're going to do another example of the work done during adiabatic compression. Okay, and then that will be the end of lecture 8. See you next time.